As we have been doing this year, we'll start with a short karakia. So please join me in reciting the te reo that's up on your screen. Kia ora te marino, kia whakapapa pounamu te moana, hei huarahi mō tātou I te rangi nei, haumi e, hui e, taiki e.
Taiki e.
And to introduce our speaker, so Dr. Simon Cox is a principal scientist at GNS Science in Dunedin. His early career was dominated by an interest in tectonics, the Southern Alps, Antarctica, and mineral exploration. During the past decade, he's focused more on geological hazards, characterizing landslides, the alpine fault, earthquake hydrology, and shallow groundwater systems. This has led him to work on issues of liquefaction in Christchurch and sea level rise in Dunedin. He has just recently published a major piece of work on groundwater in Dunedin, the result of about 6 years working with the community, Dunedin City Council and Otago Regional Council, the results of which he will present today. Widely recognised as a public speaker and communicator of science, Simon maintains close ties with local iwi Māori, supervises research students, collaborates internationally and is cited globally, and has a wide network to science end users. And over to you, Simon.
Thank you, Emily. Kia ora, everybody. Ina mana, ina reo, ina karanga maha o te wā. Tēnā koutou, tēnā koutou, tēnā koutou katoa. Ko araki te mauna whakahi, ko piki raki tahi toko mauna, ko kararo remarkables toko waka, ko kawara toko awa, ko ngati Pākehā toko iwi, no Otipoti aho, ko Simon Cox toko anoa, no reira tēnā koutou, tēnā koutou, tēnā koutou katoa. I'm just going to share my screen, everybody, and hopefully that will work for you all. Today I want to take you on a wee bit of a journey through what we've been learning in Dunedin, and I want to do it with indulging myself to show you some experiments and some movies and bits and pieces that have led me to kind of understand groundwater and the conditions in Dunedin on the basis of that. It's really is, as Emily said, it's relating to this report that we've published. I've got a picture of it here, but that's really the culmination of a lot of work and a range of different funding that we brought together. So the money has essentially come, and the science investment has come under the groundwater SIF program, under New Zealand Sea Rise, and under the Strand Marsden project. And that's shown there with some of the partners, as well, the Otago Regional Council and the Dunedin City Council and the South Dunedin Community Network. All of these people really are contributing to this, and there's a lot of co-authors that essentially would be on this work when we bring it together as a paper. We're in the final stages of doing that now. We've had a lot of data collaboration from NIWA and LINS, and EQC have been involved in as well in the past, also drawing on data from the hospital monitoring in Dunedin. So there's lots of people involved in this work, and I deliberately put this acknowledgement right at the start to get that, make sure I didn't forget. The problem we're trying to address today is shallow unconfined groundwater and how much it's going to be affected by sea level rise, and what are the hydraulic links between the shallow groundwater and the sea, and what does that do to the near surface environment? When and where will infrastructure and land become unusable, essentially? That's the kind of big scale problem for New Zealand. And it's important to just point out that this is the sort of shallow unconfined area, very different from the deeper aquifers, which depicted here with perhaps some of the ones underneath the confining layers, which tend to happen up to about sort of 40 meters below the surface at the coast in a lot of coastal places. So we're really dealing about this top layer, and the issue is got a range of different things with it, but essentially as sea level rises, it will give a sideways shove essentially to the water table into the groundwater, and it will stop the groundwater from draining through gravity. And as it does that, the effects of the tides and things that propagate in and affect the water table will shift upwards. So there's a variability that will get closer and closer to the surface. And that changes the storage potential of the land, which can affect both the infiltration and the runoff as that volume gets smaller and smaller. And as the water table rises, of course, where it intersects with the surface, we can have springs and ponding and some form of emergent groundwater. So that's the kind of the setting of the problem. And when it comes to thinking about it, I've said problem deliberately because there's a range of things that happen, and some of them are hazardous and some of them are just nuisance. And we have a whole range of effects at different depths of groundwater. So this is showing you the depth to groundwater, and as you go down in the ground, some of the problems and issues and hazards that occur, and they occur at a whole range of different places with groundwater. It's not always a direct hazard. It can contribute to problems such as an increase in liquefaction vulnerability as the groundwater gets shallower and shallower. Or you might start to get health issues as dampness and respiratory problems occur as that water table gets closer and closer to the surface. We can weaken the ground and cause more road damage as the water table gets closer and closer to the surface. And it can start to contribute to flood events and flood water. So there's a range of different problems here. And it's really important to realise that we don't have very good actual information on whereabouts groundwater causes problems, nor what the fragility functions are, or the vulnerability essentially of buildings and so forth. And they range all the way from as you're getting close to the surface to when it becomes emergent, and then even if you're causing flooding. So it causes a lot of problems in terms of thinking about groundwater. It contributes to all these issues, but it doesn't necessarily sit there as a clear hazard. And of course, groundwater varies a lot. And it varies a lot in terms of the position of groundwater and the behaviour of the water table and the rise and the fall of it are really they're very important to get on top of. Now, to do that, because there'll be a number of people who aren't familiar with groundwater, I decided to try and just focus on a couple of different essentially properties of the ground, and ones which people may or may not be familiar with, but I just want to focus on them briefly, which is essentially the hydraulic conductivity is one of them. Many people will think about the permeability of the ground, same sort of thing. It's just different terminology. And the other one really is the storativity, which is how much void space is there in the porosity and how much essentially can the ground hold in terms of groundwater. There's some other parameters that are pretty important: rainfall recharge and recession, the infiltration rate, the barometric efficiency, like how efficient does it get changed by changes in pressure in the atmosphere, and how much does it change with tidal efficiency. So they're important kind of parameters, and in order to set that up and get you thinking about them, I want to show you an experiment, and this is from some videos made by Jeff Brass, and I want to show you just some silly little playing in the sand, really, and in the sand pit to get across some of these concepts. So I'm going to show you this experiment to start with sand on one hand and gravel in the other. And I've filled them up with some coloured dye underneath, and I've put 1 litre of groundwater into each one. They're the same size glass containers. And you'll notice immediately that the water table is essentially at different heights. And that's because the storativity is different between them. We've got the water table here, and there's a capillary zone where it's partially saturated, and underneath it's saturated. And those two experiments, we've got essentially a moderately pervious sand and with moderate porosity, It's a well-sorted sand, so beautiful little grains that organise themselves very well. And on the other side, we've got gravel, which is really highly porous, and it's got big storativity, big gaping holes in between there. So then I'm going to make it rain, and I'm going to make it rain on these experiments and show you what happens and how different they are. And we'll get it cranking, and it should just go through. It does exactly what you intuitively expect it to do. You see the rain going into the gravel. You can see the groundwater water table rising, and it's going. The rain's coming at a fixed rate, and slowly it comes up. And then I make it rain on the sand. Unfortunately, I didn't really pack the sand very well beforehand. But notice how there's puddles forming there, and there's a collapse of the sand, but the water table's still rising, and in the end we get the situation where we've got essentially saturation right through, and the water table reaching to the surface. I'm just topping up the other one a wee bit more, make it the same, and the thing I've got sitting in there, which you can't see, are some loggers. So I've put some transducers in there, and I've measured the rate of rise of the water. And so the experiment on the left in the sand is shown with this curve. This is in pressures in millimeters per water equivalent. And the two bits that you saw in the rise of the gravel are shown there over time. So this is essentially a hydrograph. So the important thing to see there is that the response of the water table and the rate of rise is dependent on the storativity and the infiltration. The water table starts high in the sand and it climbs up rapidly, and we get this high rate of recharge for the amount of water going in, and that's really just a function of the void space. It fills up quicker. There's less void space, so it goes to the top, whereas the gravel takes a lot longer to fill up. It's got the higher storativity, and so the rate at which it climbs is different. If you're really sharp, you might notice that the amount of height here is 150 millimeters, and there's more than 150 millimeters here in the sand. So actually what we're doing is we get to here, and then we actually have this upper part of the curve, which is actually reflecting some sort of change within the sand as it starts to compact. So that it's a function of that experiment, and it's a bit of a problem in a way, but it's essentially taking some of the lithostatic, a component of the lithostatic load, and it's floating some of the grains essentially. So the pressure around the transducer is higher than the water level. Okay, so now we'll go to a slightly different version of the experiment, where I've put some potting mix and some soil on the top of this left-hand side. And on the right-hand side, I've made this very impervious, low storativity kind of essentially rock dust sitting on the top. And I'm going to do exactly the same thing again. And it's a slightly longer experiment. Let's see, make it rain. Yep. With this left-hand side raining through that soil, it's high. It rapidly fills up, and it basically changes very quickly. But in contrast, when you've got no, when you've got a clay type sediment or something like that, you're perching that water on top of the water table, and you've got it isolated from the water table down below for a lot of the time. But this is still rising, because some of it's leaking down the sides and so forth. But it takes a long time, and we'll sit there and watch this. You can see some bubbles of air coming up, and you'll see that it slowly gets closer and closer as that percolates downwards. You've got a downwards hydraulic gradient through this perched layer to sitting above the water table. So you've got them separated out, and then ultimately towards the end of this experiment, once enough air bubbles out and pathways gets formed, you get this very rapid connection through to the water table underneath. It should be going about now somewhere, right at the end. It sort of percolates down, boom. When it gets that hydraulic connection, you get this result. And the curves for those are shown here. There's the sandy layer increases at the same higher rate than it did before. Interestingly, it decreases with time. Either the potting mix is absorbing some water into the wood, or maybe the sand is reorganizing itself and is compacting. But you know, perhaps that wouldn't happen in a natural setting. As opposed to in the gravel, we get these sort of this rise, and we get these sort of sporadic leakage periods where it's jumping between the two, and then ultimately it kind of jumps down, and we get this whole collapse where the pressure then just goes up to the top level. So a couple of experiments to get across the concept of storativity and the importance of geology, essentially, in the responses that we see in a hydrograph. Now, I want you to think about the same experiment, but now being placed in the sea. So here's a container full of water, and we're having sea level around the outside of it. And in this case, the glass container is isolated, so you can imagine that being like a basin where you've got impermeable rocks around it, or low permeability material, compared with this one on the right, where I've got a cardboard box which has got holes punctured in it. It's leaky, it's getting wet, it's slightly permeable, and we've got sea level rise going on at the same time as we have all of those other things, as well as having a bit of topography on the coast, on the land, and rain happening in different places. And so conceptually, I think you can start to think, what would happen as sea level rises? How will it stop the flow away or the flow out? How does that affect what the water table is underneath? And that's the problem we've got in Dunedin, essentially. Oops. So the setting is sort of shown on this diagram, where we have sea level, which varies due to tides. It has the mean sea level. It has variability. It has an anomaly that might be, the long-term anomalies. Storm surge events that sit at a higher level. And then we've got the waves and the wave setup and run up on the top. And occasionally that will go, potentially over the top or cause some erosion to the dunes. Then we've got a water table that is sloping downwards towards the sea. It has a hydraulic gradient, but it has bumps and features in it that reflect the storativity of the sediment. And so it's not flat. It's not everywhere flat. It's got this subtle slope to it, and it has this variability depending on when it rains, and also at this end. But when you get close to the coast, it has a variability that reflects the tides, and the tides decay exponentially inland, depending on what the permeability of the ground is. And we've got the rainfall, which has runoff that might cause pluvial flooding, which we have at the moment, a sort of a transient hazard, essentially. But with sea level rise, we push the groundwater table up and that zone of variability, and we lose the ability to store water in the subsurface, which means that we get more runoff, which means we get an increase in the pluvial flooding, and we also have permanent groundwater flooding if that water table intersects with the surface. And that's dependent on the shape of the water table and the amount of sea level rise. But in general, depending on which model you adopt and the way you see it, the water table should essentially be long-term equilibrating with the sea level at the coast, and then having some variability there associated with either the forcing of the tides or the fluctuations associated with rainfall. Right, so in Dunedin, we measured the fluctuations in groundwater level using these sort of loggers in a network all around the flat-lying part of the city. project that was funded initially in about 2019. We set up a consortium of people, and the main person really responsible for a lot of the work behind looking after the data is Mark Etmer, shown here. That's about as much of a photo or any profile as Mark would like to give you. It's about half of his presence in a photograph. But Mark has done a brilliant job looking after this network and this data, and I'm deeply grateful for the work that he has done. So if we look at the hydrographs around Dunedin, we see a whole range of different features. So these are plotted for the 2019-2020 year. And you can see the variability, and immediately you can see, you jump out at you, these two, this one here at Kennedy Street and this one here at Tuesley Street, the bores that are really strongly tidal. They have they're going up and down every day, and so you get this sort of blue smear all over the hydrograph, which is actually a series of sinusoids. But other ones have a more, sort of subtle set of fluctuations through it, and you see that mode coming through here with the same sort of variations. Other ones have got those variations, but they've got this high noise kind of thing going on top, perhaps where they're being connected to a perched layer or where they're connected close to the surface during rainfall. So they've got a much more flashy response rather than a kind of a antecedent response. So we have all these different boreholes, and they've all got their own behaviours that reflect what the geology is, but also what the local drainage and the local impervious surfaces are. Now, John Haynes, he's on the cork. I saw him there before. John Haynes and Peter Johnson have made movies of that data, and so I'm going to show you the area of Dunedin as a movie during a rainfall event. And so here's some of the boreholes. And this is the harbour and the hillside. So this map reflects this area, and the colours represent red represents a local rise, blue is a local decrease. And we're going to look at an event when the Elton John concert was on, and everyone got absolutely drenched going to our stadium, where they stayed dry once they were there. But the rainfall started just at the end of January. Then we had another rainfall event, then we had another one on top of it. And you can see the rise here at the Anderson's Bay borehole going way up and then receding afterwards. Meanwhile, the ocean tide in red is going up and down, and one of the boreholes, Kennedy Street, has a strong tidal signature. And in fact, it's going up and down each day, pulsing with the tides. So you'll see these in this movie, and here we are. The colours, where it's going bright red is the tidal borehole at Tuesley Street, and here and down here at Kennedy Street. Those are the two most tidal bores, and there are small fluctuations, and some of these pulses come in, maybe about a 1 centimetre tide at about 1 kilometre in, and certainly a millimetre right at the back in the centre of the basin. There's a phase shift, there's a change, it's delayed, it takes a while for that tide to come in. Then we start getting this first lot of rain, and everything starts to top up. And then we get another rainfall, and all of a sudden it starts to go way above its average. And then the evening of the Elton John concert, it poured down, and it really filled up the groundwater. And we can observe this now. We can see what the effects are, which way the water flows when something fills up. It's such a cool piece of work by John and Peter Johnson generating these movies. It's just such a good way to look at it, and you can filter the data and play with it in all sorts of different ways. So the Dunedin water table is really, here's some examples again with those variations shown here over 0 to 365 days. It varies in these sort of pulses that reflect those frontal systems. And if you take the rainfall here, averaged over the last 30 days, you can see those same modes going through the data. So it's the combination of the antecedent rainfall that is driving those variations in Dunedin. Now that's quite different in other centres, but Dunedin is like that. So in this report that we've completed, we're basically trying to take all of those observations of what's happening now and capture them in groundwater surfaces and then generate models for sea level rise. And we've generated essentially 646 feature classes in a data set that you can download. It's pretty big, but lots and lots of observations of the median and the 95th percentile and the high water springs and so forth. And I'll take you through a couple of those as an example. Here's the groundwater elevation as a map across the city, showing you in colours and height above datum 2016, being very aware that sea level is actually slightly below zero. The datum doesn't necessarily reflect sea level for New Zealand vertical datum locally. And it's kind of, the way to think of it, it's a bit like a bubble sitting on your desk if you've dropped some water. These features here have topography, but they're in the ground, they're under the ground. And at high tide, it looks something like that. It's quite different. The tidal effect gets into it, just as the rain effect gets into it. So you've got these fluctuations going on from median to high and low tide. If you subtract that height from the LiDAR surface, you can get a map of the depth to groundwater. So how far below the surface is that water table? And you see that there's an awful lot of Dunedin, which it's got very shallow, around about 1/2 metre of below the surface. You'll find the median level is always sitting there. So we're very close. The water comes up very close to the surface in many places. But luckily we're protected from the Southern Ocean by these dunes. And we're protected from the harbour by this reclamation. So this is an old shoreline along here, and we've got this high land and the high land here. And there always has been the concern of, well, what if the tides push water in? And what we found then, obviously, is from the movie, is that only some places are really strongly tidal, up here and down here. Now, let's go back to that experiment. When we poured water on, we could see the rate at which the water table rose. This map shows you the rate at which the groundwater rises at each of the boreholes relative to each millimetre of rain. So it's what I'm calling the rainfall recharge, or the index. It's the ratio of the rise of the groundwater table to the amount of rain, and in some places it reaches 10 times more rain, more rise than rain, and that's because they're muddy sediments, they're the clay-rich ones, whereas places where it's sandier have much lower recharge, just as you had the difference between the gravel and the clay in the sand in the experiment. Now we can take that and we can calculate the subsurface storage, and this map here shows you at the current rate whereabouts do we have no room to store rainfall of different amounts. And you can look at the 12-hour rainfall at the average recurrence interval for a 2, 5, 10 or 100-year rainfall, and this is just the one that I've taken. It you could use a 24-hour one or a 6-hour one, but essentially what I've done is saying, say for example, a 10-year return period would be a 60, I think from memory, a 60 millimetre rain event in that 12 hours. And so I'm saying, where would that fill up? Where do you have no storage left? And you can see this as a map, and you can see the uncertainty going outwards depending on the increase in rainfall. Now we can then add sea level rise to this, and I'm going to show you a movie, and I'll crank through it and watch for the change in that's 10 centimetres, 20 centimetres, 30 centimetres, 40 centimetres, 50 centimetres, 60 centimetres, 70 centimetres, 80 centimetres, 90 centimetres, and 1 metre. So what that's saying is that after a metre of sea level rise, you don't have any storage capacity in the ground anymore. Now, you may not have needed it because there might have been runoff anyway, but essentially you're saying that if you don't want to pond the water, you're relying on the stormwater network to take it all away. And it may not be realistic, especially after a metre of sea level rise, for something that's gravity dependent to take that water away. But it's saying about the loss of subsurface storage as the water table rises, and where you get increasing dependence on the stormwater network. Now we can also map in the same way, we can map out what happens with emergent groundwater, and you can see it takes a bit longer, but you can start to see where high tide might start to reach to the surface, and then you start to get a different color and where perhaps the median level might reach to the surface, and then it increases up to 100 centimetres of sea level rise, where you're starting to get emergent groundwater on the median level or on mean high water springs, pretty much during every day. The water table you'd expect to reach to the surface, or some of these other values in these other colours are representing storm surge and how a storm surge might propagate through there. I haven't got time to go right into the modelling of that, but it's essentially using the tidal efficiency and equilibrating it with sea level. Now, finally, I want to show you one more movie of the coastal inundation, and this is NIWA's calculations based on their storm surge, extreme sea levels, and how that looks as you increase sea level rise. So here we are, 10 centimetres, 20 centimetres, 30 centimetres of sea level rise. We're getting some of these storm surges will get to there, and then all of a sudden, boom, the water gets in over the top of the elevation of Portsmouth Drive, and all of a sudden we have the ability to inundate the city with storm surge. So what we've done for this multi-hazard forecast is to take these different hazards, or problems, if you want to call them that, or contributions of groundwater to problems, and we brought them out over time, essentially, or over increments of sea level rise, just as I showed you in those movies. And here you can see the relative timing of these different events, and that's the key to it, is understanding the relative timing and how one leads the other. So the effect of and the loss, the impact on the amount of area of land due to the loss of storage happens before we start to get problems from emergent groundwater, which happens before we have any real coastal inundation. And the reason I've given it in terms of sea level rise increments is that we don't know what range of time that might be. So for planning, we need to have some ideas of the time frame, but even 40 centimetres of sea level rise, it could be 2077 or it could be 2126, depending on whether we curb our emissions. So in this report, we've deliberately worked to the physical state, and then we use a lookup table so you can have the range rather than carrying this uncertainty of human behaviour into the calculations. So we stick to using these physical limits. And here's some of the curves just shown on a graph to get you to think about it. So it's the percent, if you look at the percentage area where there's some exposure to a problem. So in this flat area, 9.6 square kilometres, what's the percentage area that's affected? And you can see the differences in the curves. So here's rain exceeds storage. And I've just taken the ARI 10 at the 95th percentile level of groundwater or at the median. And there's the median going up there, and this is the curve for the 95th percentile. And so you see that we currently have a problem already with rainfall and with flooding. And the 2015 flooding was essentially a combination of a whole lot of factors. Probably not actually the groundwater being involved that much, but we had problems with the stormwater system at the time. But then you see that the emergent groundwater ranges between here at the 95th percentile, if it's coming from 95th percentile level, or the median, or the median at storm with an extreme sea level storm surge, or the median if it's a sort of static condition. So we've got a band in here of the emergent groundwater things. And the shape for the curve is very different for the coastal inundation. You see the step type function, and that's because of the level of the reclaimed land holds it back until it suddenly overtops it, and we get this different profile. Now, that's quite important when you start trying to work with these things, because if we got too involved in trying to invest in the stormwater system, we may only have about 40 or 50 years or less before we get groundwater emergence. So in terms of infrastructure investment, it makes it quite tricky if you have one hazard, then the next, and then the other one, and you're trying to deal with them all. But if you don't actually have those clearly outlined in terms of what leads and what follows, it's really hard to justify work. So the sort of forecast for Dunedin is that we're going to have this rise of groundwater, and the ability for the rain to be absorbed, or for the ground to act like a sponge, decreases. And so this exacerbates the rain-related flood issues, and that's probably going to sit there for the next 30 to 40 years as our dominant issue. And we'll have 2 or 3 flood events where people will be worrying about that before we even start to see groundwater starting to come out of the ground. But then eventually, as the water table gets closer to the surface and its variability is there, we're going to get these extreme sea level or high tide events that are going to cause some emergence and some springs and some seepage. And then that will eventually turn into something that's quite permanent. So by the time you're getting up to about maybe 60 centimetres of sea level rise, you've got about perhaps 18% of this land area where we would predict some form of emergence or seepage or groundwater at the surface. And then we have coastal inundation coming in over the harbour, over the top of the reclaimed land, depending on whether it's a 1 in 100 year storm surge or 1 in 10 year storm surge, and so forth. And so we get this kind of event at the end with coastal inundation. So the groundwater is contributing to all of these problems well before coastal inundation throughout most of the centre of the city. Now, there's a lot of assumptions in this, and you have to come in there with all the caveats. The first one is that we're assuming that the dunes are there and we've got protection by those dunes. If those dunes go, then all bets are off. If we get a tsunami and then a storm surge and it erodes away quickly, those dunes not there, it's a different story altogether. The coastal inundation will occur a lot earlier. So similarly, if there's mitigation done, if they raise Portsmouth Drive, that could, this is assuming no mitigation. So it's using this now forecast into the future, and it's assuming that the stormwater and wastewater networks, the performance of them now will be similar in the future, and you don't know that for sure. We're mapping exposure to these processes. We're not necessarily mapping hazards and risk, and that's something that we have to be very careful about, because it might just be a problem. Just because groundwater seeps out of the ground, it's not a hazard to life, for example. It's not going to kill anyone. It's not going to be happening at a velocity that's going to be injurious to people. It might cause damage to houses, but it may well cause problems well before that, in terms of, for example, making subsurface stormwater systems leaky and fill up so that they don't function as well. So we really don't know anything about the vulnerability, and that's something that where research needs to go. So in summary, we've used a comprehensive groundwater monitoring network that we've installed to get information about what's happening now. And ORC have been amazing at both investing in that work and in looking after the data sets and providing that data and doing that monitoring of what's happening. I believe that this is world-leading science because it's thinking about a multi-hazard approach to the thing. We've got quite distinct hazards or problems, and you need to be able to look at it all together rather than going on one or the other, because otherwise you'd be investing and trying to invest in major infrastructure and replacement or even be thinking about other adaptation options or managed retreat or other things. Any of those plans, they'd be occurring over a relatively short window, and just too small to get your return on your investment. But more importantly, perhaps, it's really important to get on this episodic versus permanent processes. So often when we deal with groundwater models and looking at hazards, we often we might say, oh, groundwater's come to here and it's going to flood. But in the meantime, on the way to getting to it permanently being there or permanent flooding, we have a lot of events and episodic things that occur once every 10 years, once every 100 years, or 1 in a 100-year event beforehand, before it actually gets right to the surface. It's really important with groundwater because it varies. The other part of the study is that it's essentially, because we've used the groundwater monitoring, we've got precision at site-specific level. We're pretty confident that we've actually understand pretty much where the groundwater is going to be across the flat-lying areas of the city, and we can say at a property scale roughly what's happening. We've found that the ground is less permeable than we thought it was, and that there's a lot less tidal response than we initially thought there would be. Only 2 boreholes have got strong tides and strong tidal efficiency, but most of it's actually impermeable clay, and hence that's the problem in terms of flooding from pluvial related processes. The rainfall causes the surface flooding, and this is carried then from this kind of putting in the network, investing about $100,000 into the subsurface information gathering, and then maybe another $100,000 of sort of gathering the data and collecting it and things like that, carrying through, taking the science, and we've got a whole program in Dunedin around the South Dunedin Futures program around adaptation and solutions and what they're going to do about it. So what this study has done is it feeds into this whole South Dunedin Futures program, which is taking in a dynamic adaptive planning process, and we're feeding in what is happening. Then there's a lot of community consultation to be done about what matters most and what can we do about it, what are our options, then make that happen, and then to review, where are we at in that whole kind of cycle of dynamic adaptive planning. And the community are deeply involved. The DCC have got the community deeply involved in it. Just to finish on, I just want to touch on something it's something that's I've become much more aware of lately, and that's the importance of events and the recurrence between events, and then also the whole episodicity of hazards and events on the way to becoming hazards. And I've just stuck this up to as an example, which was one of the boreholes back in May through to August 2022. It's a hydrograph down at Tahuna Road. But during the winter, we had these events that a bit of a rainfall event, and then another rainfall event, and then before it had a chance to recede, another rainfall event, and it nearly got to groundwater. It was nearly emergent at that point, and then it started to recede, and then we had this other event and it got to the surface, and it just essentially sat right at the surface very briefly before it started receding. Now, if this event here had occurred a bit sooner, we would have had a different profile at that location and a lot more water contributing to the flood water. It highlights the issue that we have as a fundamental hypothesis for our Marsden program. And it's shown on this beautiful diagram that Greg Bodecker put together with Ivan Diaz-Rainey, which is showing you an example. It's not anything real or anything. It's a hypothesis over time that as the groundwater rises and gets closer to the surface, if the rainfall gets through and gets connected to the surface and connected to the groundwater, then we have these spiky rainfall events sitting on top. And this one might represent, a flood event where we've got some inundation because the groundwater has done essentially what I just showed you in that previous slide. It's got, essentially out over the top, and that water contributes to surface flooding, or may pond there. Now, with climate change, we're bringing in more moisture, and these events, these rainfall events, are going to get closer and closer together because we're changing that whole profile of our precipitation, but we're also lifting the base from which they're causing problems. And so as you go, you might start to get some health issues. And you might start to get some assets stranded where, for example, you get the groundwater so close to the surface that you can no longer flush the toilet because the pipes are full. And then eventually you might get groundwater poking out and inundating it. Now, in a lot of the traditional work for risk assessment, we often tend to take this point and we go, right, this is what the asset values are, and this is how much we're potentially losing, and we go from this point, and we basically say what's the percentage of, what's the value of the property that we're losing at this point. But on the way to getting there, if you look at house values, the hypothesis that we have is that the house values get affected by these event frequencies. So here's the house value on a property. It's rising with inflation, and then we get this flood event, and it drops the price of the house, and then it recovers afterwards, and starts to come back up, and then we get another flood event, and it drops and then rises again, and so we get this sort of sawtooth type behaviour as it goes up and down, but generally is rising. But as these events and the frequency gets closer and closer, then the time for the recovery gets less and less, and it can't recover. It's like the borehole the water doesn't get time to flow away. Well, similarly, you don't get time to recover, and so you may fall below the comfort zone for banks lending money or for insurance to insure the property. So you might first get insurance pull out, and then you're limiting who can borrow money. So you go up and down like this, and then you might get to the point where essentially the house value gets written off. And our hypothesis is that all of this can happen well before groundwater actually gets to the surface. So there's all of these event type things that occur through here. And we've got some data on this. Quinn has written a paper, if you're interested in it, on the Dunedin drop and recovery from the 2015 floods. And we're working through this whole process of sort of testing this model for part of this Marsden program. So why do I highlight that? Well, it's the thing is that as climate change kicks in, we need to be socially aware of how we have these approaches in adaptation. And it's the events that cause people to, it's these episodic events that cause insurance to pull out and banks to do things. We can sit there and do these asset calculations for the permanent condition, but it's the transients and the way that people develop resilience that actually that matters, and the way that we will respond. And so it's these episodic events and the return of them that are really important for how we deal with climate change and how we, you know, how we do different responses to it. And often we're not, as scientists, we're not dealing with that episodicity appropriately enough so that we can give indications of it to feed into some of the social science work and just what's happening in terms of how the community responds. So to me, it's really important to deal with this. And I'm quite pleased with the way that we've actually managed to show that both the episodic and the permanent conditions in these models for Dunedin and the multi-hazard aspects of it, which actually provides a pretty good picture of what's happening for this process. And that's what the new report does. And so you can sort of get it off the web shop if you wish to have a look at it, download for free, or the data as well. So I think I'll leave it at that and take some questions. I've used most of my time, but not all. Yeah, we'll hopefully that's given you a bit of an insight into some of the work we've done.